right, so I'd like to introduce your knowledge proofs with a couple quick demos of them, because the definition's a little long and it's easier to just see who they are. So can I have a volunteer? Okay. So I've got two coins here. They look pretty much identical. I'll let you take a peek. That's not perfect, but I claim that I can distinguish between these.
Okay, I'm just verifying.
Yeah, they're basically the same. Yeah. Okay, great. So here's what I'm going to have you do. I am going to have you take these in the hands I'm giving them to you. If I remember that. Put them behind your back. I'm not going to look, and then either switch them or don't, but keep track and make sure the people behind you. And then just give me the one in that hand. The end there. Let me take a quick look. You did switch them. Cool. So I'm trying to convince you that I can tell the difference between these coins. How convinced should you be so far? What do people think? No. Not very. How, if you had to put like a percentage on?
50-50.
50-50, right? Like if they are the same, I only had a 50-50 chance of getting it. Okay. So let's just repeat.
Can I ask a clarifying question?
Yep.
So you said they're basically the same. Did you just say basically,
Well,
or are they actually the same?
I would like them to be actually the same, but nothing in the real world, like two objects are actually the same. Yeah. We're going to be moving to the digital world soon, where zeros and ones can kind of do a better job. Have you done or not done the thing you intended? Done or not done. All right, send it over. Yeah, let's see. You switched them again. Okay, how convinced should you be now?
50-50.
50-50.
75-25, right?
Yeah, so if the 2 coins are truly identical, then these are actually independent events that are happening. Right? Because I'm just guessing each time. So my odds of guessing correctly twice are only 25%. Maybe closer to 75%. Let's do it one more time for good measure. Okay, perfect. All right. Should have done a better job keeping track. You didn't switch them. Awesome. Great. Okay, so how convinced now? One more little math.
Well, you look pretty surprised that time, so.
12.
87.
It's early in the morning.
No, that's all right.
Yeah, cool. It's a 12.5 chance that I just guessed each time and got lucky, so there's only, or you should be something closer to 7.5. Awesome. So hopefully you believe that we can just keep repeating this and get you as convinced as you want. If I did it 100 times, how convinced should you be? What are my odds of just guessing correctly 100 times in a row? Yeah. 1/2 to the 100. Which, I forgot to do my prep, but like, how many atoms are there on Earth? Like, I think less than this many. I think this is a huge number. Yeah. Anyway, you should be pretty convinced, like about as convinced as you can be.
Number of atoms in the world is around 1.3 times 10 to the 50.
10 to the 50? Okay, so it's not quite there, but it's getting pretty close.
Yes, still a very big number.
Yes. Okay. All right. I need another volunteer for my next trick. Anyone want to be convinced of something? Awesome. All right. So I want you to pick a card and I'll look at it. Or actually, before you do that, did you verify that this is a full 50 card deck? I tried to make it easy for you.
Can you repeat what's going on? Sorry.
I am going to have him. Currently, he's verifying that it's a full 52 card deck. I've got the tricks up my sleeve. Sleeves, in fact. And once that's done, he's going to pick a card and not show me, and then I'm going to prove to him something about it.
Okay.
All right, put it face down on the table. Here. Cool. Okay, so I'm going to show you something about your card. Don't look at it. Cool. Here are all the black cards. Could you just verify that really quickly? Cool. So what do you know about this card that's face down right here? It's not black, so it must be red. Cool. So in the last trip with the coins, I was able to hopefully convince you that I can tell the difference and that there is a difference between them, but you don't know anything about what that difference is. And likewise here, I was able to convince you that your card was red without telling you anything about whether it was a diamond or whether it was a heart or what number it was or anything like that. All right, this last one's a little bit more involved. Can everyone see the surface of this table?
Yeah.
Okay. So who here knows what sudoku is? It's the puzzle. It's kind of on a 9 by 9 thing. You can only have one number of each number between 1 and 9 in each row, in each column, in each 3 by 3 grid. So 9 by 9 is a bit too big for practical purposes for demoing, but hopefully you can see how this would work for that. I'm going to do a 4 by 4 sudoku. So just the numbers 1 through 4, 2 by 2 grids, all the same rules. And I'm just going to draw up here. So 4 by 4 sudoku is like really easy. So like, I guess think of how I would do this with more. Okay, here I've got my 4 by 4 sudoku, and I'm going to start. The sudoku puzzle comes with some of the numbers revealed, and then a solution is what are the rest of the numbers, such that every row has the numbers 1 through 4, every column has the numbers 1 through 4, every 2 by 2 grid has the numbers 1 through 4, and I've got to use 1 there, 3 there, and 3 there. All right, so I'm going to convince you that I know a solution, but I'm not going to tell you anything about that solution. So it's just, if I have some big puzzle, I'm like, oh, I made this puzzle, I want you to try it. You're like, it's probably impossible, and I'll be like, no, it's not impossible, you should try it. So, okay, I'm going to start by picking one of these cards at random. These cards just have permutations of 4 numbers on them. I would have done all of them, but they're like 24, and I don't want to do that much prep. Okay, so I picked one at random. Which one is that? It's this one. Okay, great. So I'm going to put that here. And then I'm going to put, so when I put in cards face down on the table, you should think of that as me sending you encrypted versions of whatever's on the other side. So, okay. Double check that this isn't typing yet. Okay, great. Yeah. Okay, so I'm going to start sending you little encrypted messages. Indices of where everything is going. All right. So I've sent you a full encrypted solution. Now here's what you're allowed to do. You're allowed to ask me one of 4 questions. You can ask, can I see the rows? You can ask, can I see the columns? You can ask, can I see the 2 by 2 grids, the squares? Or you can ask, can I verify your set? My set. So verify that I really do have the number 1 here, 3 here, and 3 here.
You say, are you saying 1 column, 1 row, or 1 2 by 2, or?
If this was going to be done on computers, that is what I would mean, but I'm going to use a physical trick here so that I can do all the rows at the same time, all the columns at the same time, that kind of thing. But yes, good question. So you have 4 things that you could check. Which one do y'all want to check?
Rows.
The rows. Okay, cool. So here's what I'm going to do. Is I'm going to take my rows and shuffle them up So this is something that doesn't really have an analog on the computer.
Gotcha.
So if we were doing this on a computer, I would have you check one row, one column, one 2x2 grid,
Yeah.
or my setup.
Okay.
And you would have like 13 choices or something. Is that right? 4 plus 4 plus 4 plus 4? Yeah, 13. Alright, some shuffling there. Pretend I'm a good shuffler.
So you're taking each row, shuffling it, and then you're going to.
Yep, and then I'm sending this over. If you would like to just verify, you should see the numbers 1 through 4 in a random order. If you don't see the numbers 1 through 4 in a random order, then that means I cheated and one of my rows was not correct. Because I can just show you space up. Everyone can verify. Yay! Cool. So hopefully that convinced you that whatever I had put down there just now, the rows were correct. Or at least the rows followed the rules. Now, just like I asked with the coins, how convinced should you be? What was the chance that if there wasn't a solution, that I just got away with a little trickery? If there was no solution, what were the odds that you caught me cheating?
We only get to look at one row, though?
Well, here, let's talk about all the rows, or all the columns, or all the squares, or my setup. There are four things.
4 options, right? So it's probably 1 of the 4.
Right, because if there's no solution, one of those 4 would have to be wrong, right? If there was a solution, I would be able to satisfy all 4 at the same time. At least one of them I cheated on. Either I have a solution to a different puzzle, and so my setup is going to be wrong, or I have one of my rows where I cheated, or one of my columns where I cheated, or one of my squares where I cheated. Now, with Sudoku, actually, it's impossible to violate just one rule, because it's Sudoku, so it's actually going to be even more than 1/4, but for purposes of just bounding things and making things simple, you had about a 1 in 4 chance of catching me, say, which means I had a 3/4 chance of getting away. So if we do this again, and I succeed again, what were my odds then of succeeding twice in a row? Yeah, it'll be this, and then again, right, times, if there's no solution, I have to cheat again. So each time we do this, we multiply these together. I think this is about 0.52 something. So we started with a 75% chance that I could get away with it. Getting away with it twice, only a 50% chance. And now if I do it 4 times, it'll be kind of just like the coin problem from earlier, because I had about a 50% chance of getting away with it each time. So maybe we have to do this 200 times. But at the end of the day, I can convince you that I actually do have a solution, hopefully, to whatever probability you want. Y'all want to see the demo one more time and like check my setup just to make sure it's clear what I mean? I think actually it would be a good demonstration for something we might want to do later, how these permutations are working. So I'm just going to pick another one. Okay. So I'm going to set it up one more time. I'm sending you encrypted messages. This time there won't be any shuffling, so it will be just like in the real world. And I'm also sending you an encrypted message of what my permutation is, by the way. It's also one of my face down cards.
What does that mean in this context?
Yeah, so say that I sent you all of these in my encrypted solution. If you check a row or a column or a square, then I'm just going to decrypt those things. I'm just going to flip them over in place. So for example, I mean, it's not going to be zero knowledge if I do this and, but I don't want to set it up twice. So and I do something like this. If you ask for this square, I just send you the keys to decrypt that row or that column or that square. You can see. But you might worry, like, am I not revealing something about my solution? And my answer is actually these are going to be in a random order because I changed my solution to be random beforehand. And what I mean by that is if you want to check my setup, what I'll do is I'll reveal the things from my setup, and I'll reveal my permutation. So here you can see that 1 goes to 2, which means that this top corner is going to be a 2 instead of a 1. And you can see that 3 goes to 1. So that means that the things where you should expect a 3, you'll find a 1. So this shows you that my setup is actually correct. But since I'm choosing a new permutation each time, if you're not checking my setup, then you're just getting 4 random numbers. Because I've permuted them randomly.
Yeah.
And so this is how I'm kind of not revealing anything. Each time, I'm going to just flip things over in place, a row or a column or a 2x2 square. And then each time I'm going to pick a new permutation.
Okay.
So to be clear, we have to check the setup every time. And then
No. You get to either check my setup, or you get to pick a row, or you get to pick a column, so on and so forth. Because of those 13 things, at least one of them has to be wrong if there's no solution. And so you have some chance of catching me, so my chance of success is less than 1, which means if I take a big enough power of it, eventually it'll be as close to 0 as you want.
All right.
Because taking a big exponent of a number less than 1, it goes to 0 very quickly.
Wait, so why did you have to transform each number?
Because if I use my actual solution each time, the same one, then when I reveal the row, you remember that row, and then you ask for the next one, and I reveal that, and so on and so forth.
And you can build it yourself.
And you could just learn my entire solution. But since I'm permuting the numbers each time, that means that each time you just see the numbers 1 through 4 in a random order.
Yeah,
You're not learning
You're
anything.
just proving that 1 through 4 is
Between-
in that row, column, or 2x2, and not showing your order that you actually have for the solution.
Yeah, it's kind of like how when you asked for the rows, the first time I did it, I shuffled everything. Essentially, I'm shuffling beforehand.
The shuffling is the permutation.
Yeah. Any other questions? Cool. So in general, if the prover has a chance of failure, then that's going to be enough, and we're just going to repeat a bunch of times, and eventually their chance of succeeding every single time you did it is going to be as small as you want it to be, depending on how many times you force the prover to do it.
I know it's a bit of a semantics thing, but is this technically a proof? Because it's just a very high probability it's a proof.
Yeah, so let's define zero-knowledge proof now. We've seen a couple demos, and then I'll make you come up with a few. So, here we're using proof in a very computer science-y way, and not so much a mathematical one. Zero-knowledge proof is going to be an interactive proof, which is zero knowledge. I'm going to write much more than that down in a second, but interactive proofs are probabilistic proofs. They're not, like, necessarily ironclad in the same way, but, you know, how certain can you really be of a written proof anyway? You know, we could have a philosophical argument later over, like, whether all proofs are probabilistic proofs at the end of the day. But okay. A zero-knowledge proof is a conversation between a prover, in all of these cases that was me, I was the prover, and a verifier. In all of these cases, that was one of you or all of you, which is convincing of some fact and which is zero knowledge. So I have to tell you what convincing means, and I have to tell you what zero knowledge means. By the way, can everyone hear me? Do I need to use a mic here?
no, you're good.
Okay. Great, because I don't want to use a mic. Okay, so convincing means that a dishonest prover is this getting too low? Should I like bring it up somewhere? I'll say it out loud as well, so you can ask if you can't see something. But a dishonest prover may fail and an honest prover cannot fail. So far, I haven't said anything about zero knowledge, but all of the things we've done so far, if I was lying to you and the statement that I was trying to prove to you was false, then there was going to be some significant chance of failure. Significant doesn't have to mean like more than 1%, but it can't be like a negligible, like the same as the probability of guessing the private key to a public key kind of number. It's got to be a significant number in that sense. So 1 in 100, for example, still a significant chance of failure because we can repeat, 1,000 times and all of a sudden we're all good. Because 99 over 100 to 1,000 is still pretty small. Okay. And then an honest prover has to always succeed, otherwise this doesn't really work. Maybe I should write it instead of a double negative, I should say that an honest prover always succeeds. Great. Okay, and so what's this zero knowledge thing? I'm going to give you a bit of a vague definition for now, and then we're going to kind of iterate on it and make it a bit more precise. But to start, I'm just going to say that the verifier learns nothing useful other than the statement being proven. Sorry, I kind of ran out of space here. But okay, so the verifier shouldn't learn anything other than whatever it is that the prover is trying to convince them of. That one statement. Anything useful anyway. So looking back at our examples with the coins, what is it that I, the prover, told you, the verifier, each time?
What did I say?
That you could tell it.
What?
That you could tell it.
Well, that's what I was trying to prove. But on each iteration,
Whether or not you switched.
right, all I told you is whether or not you switched. Did you learn something each time when I told you whether or not you switched?
Yes.
What?
Oh, nothing about how you did it.
Sure, all you learned is that I can tell the difference,
Yeah.
right? You didn't learn anything else. And why is it that you didn't learn anything else? It's because I told you something you already knew, right? You knew whether you'd switched it or not. So nothing I said to you revealed anything to you. You learned nothing useful. You can't walk away from this conversation and do anything that you couldn't do before, other than claim confidently that I can tell the difference between these two identical looking points. Similarly, for these cards, I guess actually let's come back to this one because it's an interesting case to learn. And for the sudoku, I claim that I either just showed you a random permutation of the initial puzzle, or I just showed you the random numbers 1 through 4. And I claim that all of that is useless information because it's not like you can go do something you couldn't do before talking to me. You can generate your own random numbers between 1 through 4 and your own random permutations of the puzzle. You don't need a prover for that. I didn't give you anything you couldn't have generated yourself. Any questions before we move on about our current working definition about what a zero-knowledge proof is? Does anyone know any examples that we care about here at this conference of zero-knowledge proofs? What can these be useful for?
Signatures.
Yeah, a digital signature is a form of zero-knowledge proof. I prove that, originally it's just showing that I know the private key to this public key without revealing anything about my private key. But you can also throw a message in there, and it's a proof that whoever knows the private key to this public key has signed this message. Any other examples? That's the main one. It's the main one we'll talk about today as well. But there's also these things called bullet proofs that some people care about, which are a proof that, say, if all the transactions were encrypted somehow, I could prove to you that whatever was in this encrypted transaction, the outputs in total value were less than or equal to the input total value, so I'm not creating new coins. So when people try to invent side chains, like I think Liquid does some of this, or other things like that, where the transactions are confidential, so to speak, or encrypted, then you still want to prove that everyone is following the rules. So everyone has to prove that they followed the rules, but they don't want to reveal the thing behind all of the encrypted data. And so they're going to use zero-knowledge proofs. And there are other things, but I just wanted to kind of throw that out there before I move on. Digital signatures and kind of identity, like proving that you are the person who knows this secret, is kind of going to be our main focus today. Okay, so I'm going to say one last thing, and then I'm going to set all of you off in your groups to try and create one of these zero-knowledge proofs. All right, so I'm just going to show you how I would kind of notate the zero-knowledge proof that we did with the coins. Yeah? So we've got a prover and a verifier. I'm the prover. Maybe I should put this higher up. You're the verifier. And it's a protocol, and I'm just going to kind of draw arrows back and forth of what the messages that were sent. So we have these coins, coin 1 and coin 2. Now in practice, you might have noticed I only ever looked at one coin at a time. So like 2 coins exist, but really what happens here is, well, there are a couple ways I could write this, but okay, so the verifier starts by picking a random permutation of the numbers 1 and 2. So there are only 2 permutations of the numbers 1 and 2. There's do nothing, and there's switch 1 and 2. So by permutation, I just mean a rearranging, a shuffling of 2 things, and there's only 2 ways to shuffle 2 things. You can either do nothing, or you can switch them. So, okay, I'm gonna write, okay, now don't be scared. Unfortunately, permutation starts with a P, and P is used for too many things, and so cryptographers use the Greek P, which is a pi. That is not a number, that is just a thing that starts with P, in this case, a permutation. And the last time I did this workshop, a couple days ago, to avoid this, let the audience pick the letters, and that went horribly. So I'm going to pick the letters this time, because they picked letters that conflict with all of the letters later, and so anyway, I promise that if you can get over your fear of that symbol, it's just a letter for now. Okay, but this is a random permutation. Of C1 and C2. And then I could write that you sent me the permutation of, say, C1. That's what you did, right? You gave me the coin in your left hand after you switched or didn't switch them.
So you're just sending the index of C1?
What's up?
What is the permutation of 1?
It's either going to be C1 or it's going to be C2.
Coin 1 and coin.
Yeah, so pi is just a function that takes in a coin and gives you the coin after the shuffling, basically. You could think of pi as just a shuffle function. Cool, so you gave me the shuffled C1, and then I have to respond with my guess of what the bit is. So I'm going to use little hats for guesses, B for bit. This is either going to be a 1 or a 2. Right, and so if it was 1, that would mean that you didn't switch them, and if it was a 2, that would mean you did switch them. But anyway, this is just a way of writing down a conversation, and then you check whether, so actually I'm gonna write pi of C1 equals like CB, and then you check whether my guess is the same as what it actually is. So whether B hat is the actual output. Did I get which coin it was correct? Any questions about this way of writing things down? It's just on the sides I write down what the verifier is doing and what the prover is doing. And with arrows going back and forth, I have the actual conversation of what was said. I had to change things a little bit from literally what we did because I want to write it for like how computers would have done this. Right? Computers, we don't have physical things and swaps, we have like some stuff and permutations of it.
C1 and C2, are you, that's a reference to the coins themselves, or that's a reference to like C1 is always that coin I was given in my left hand?
So C1 is like the one that started in your left hand before you shuffled, and C2 is the one that started in your right hand before you shuffled, and then pi of C1 is after you shuffled. What's in either?
C1 and C2.
Sorry, that's where
Like
C1
when you
went.
gave them.
Yeah, sorry.
C1 and C2 are the way that you gave them to him.
Yeah, so you can kind of ignore the C. It's going to be like pi of 1 or pi of 2. It's just swapping two things. We're not swapping two things. Okay, so I've shown you how to show that C1 does not equal C2. But I did it kind of physically, so I'm going to pick an example now. We're going to do something very similar. We're going to show that two things are different from each other. But instead of using physical coins, I'm going to use something that's like encoded in a computer so that this can actually be rigorous and make sense. So I'm going to make sure we all know the bare minimum we need to about these objects, and then I'm going to set you loose to try and figure out how to prove that they're different to a verifier. I don't know if everyone can see this, but what do people call this object? It's got some dots and some lines between them. A graph. A graph, that's what we call it in English. Yeah, so it's really confusing because graph also means like, you know, a plot with X and Y, and you draw things, and that's what my workshop on Wednesday was about. It's a bunch of stuff with those kinds of graphs to do secret sharing, but today, when I say graph, I mean these things. So think like the Lightning Network. A graph is a network, basically. It's got nodes and it's got edges for connections. And a graph can be stored in a computer in a couple different ways. What are some of people's favorite ways of storing a graph in a computer for those who've dealt with it before?
Database.
Got you. So like a linked kind of structure in memory.
Circuits can actually be considered graphs.
True.
You're saying you can just store all the connections?
Yeah, I could somehow label my nodes and then store which ones are connected and which ones aren't. So my favorite way of doing that is in kind of a matrix. I'm realizing I don't want to write down a matrix for this graph because there's just too much going on. So I'm going to make a smaller one. Okay, but say I just have this 3 nodes. One of them is connected to 2 of the others. Okay, so I'm going to start by labeling them. Say 1, 2, 3, just giving them some order. And then I'm going to have a 3 by 3 matrix. 3. And then in each spot, I'm going to put a 0 if they're not connected, and a 1 if they are connected. So 1 isn't connected to itself. 1 is connected to 2, so I'm going to put a 1 there. 1 is not connected to 3, so 0 there. 2 and 1 are connected. 2 is not connected to 2. 2 is connected to 3. 3 is only connected to 2. So I have this matrix with 0s and 1s, where the 1s represent connections between nodes, and the 0s represent 2 nodes not being connected. But what if I labeled them differently? Yeah, so what if instead I labeled this one 2, and I labeled this one 1, and I labeled this one 3. So if I permuted my labels, I would get a different matrix, right? So in my new one, 1 would be connected to 2 and 3. 2 would be connected only to 1, and 3 would be connected only to 1. So it has some similarities, right? They have the same number of 1s and 0s, but they're all in different places. Any questions so far about, we have these things called networks or graphs, and we have this way of writing them down, where once I've labeled all of my nodes, I've given them names and order, then I can write down just a matrix of 0s and 1s, saying which ones are connected to which other ones.
So, those ones, 0, 1, 1,
that's for this other labeling here. 1 is connected to 2, and 1 is connected to 3.
okay.
Yeah, so I'm just saying if I picked this other labeling, that I've kind of circled in purple here, then I get this other matrix. So different labelings of the same network give me different things. Now for this small example, you could probably, if I gave you this and I gave you this, you could like figure out that they were the same thing. But say that I took like the whole graph of the Lightning Network, or some much, much larger network picture, and I labeled it in 2 completely different ways. I labeled it one way, and then I took a random permutation of the nodes, and I labeled it that other way, and I spit out two matrices. It's not going to be easy to tell whether they represent the same network or not. In fact, it's computationally hard, in some sense. When I say computationally hard, I mean similar to how it's hard to compute a private key from a public key. Yes, if you had infinite time, you could just try every one until you reach that private key, but that's just not going to fit into the time that we have here in this universe. So similarly, if I pick a large enough graph, it's going to be computationally hard for someone who didn't construct the problem, who doesn't already know a secret, to tell whether two things are the same or different. So how I might write this is I've got my initial graph with its initial labeling. So this here I'll call M1. And this here is M2. And I might say that it's like some permutation, pi, of M1. M2 is some permutation of M1 in this case. And when there is some way to have this pi just switches, it sends 1 to 2, 2 to 1, 3 to 3. It's just a shuffling of my labels, of the numbers 1 through 3 in this case. So when there is such a permutation, such a shuffling, we say that M1 and M2 are actually the same thing. We say that they're equal, but we put a little mustache over the equal sign, because they're not literally the same thing, but they represent the same thing. So we have this symbol for that. Okay, I'm finally ready to stop talking and give you something to do. So now what you're going to try and do, drawing inspiration from kind of our coin example, because in our coin example we're showing two coins aren't the same, I want you to show, so both people have access to M1 and to M2, which is just a giant box of zeros and ones. And I, the prover, can tell the difference between them. But you, the verifier, cannot. And I want to convince you that these are actually not representing the same network, that they're representing different networks. But I want to do it in zero knowledge. Yeah, so one last thing before I set you off. The prover, for now, while we're talking about this problem, they can do anything that they want. They have unbounded computation time. They can do really impractical things. They've got all the supercomputers. They can brute force stuff. But the verifier is running on a potato-powered toaster, and they can only kind of like, I mean, it's big enough to store M1 and M2, which they have, and they can like run through it and do kind of polynomial time things, if that means anything to you. But otherwise, they can only kind of do simple operations, like checking that two things are equal or that kind of thing. Cool. So your goal is to, I need a little mustache, is you, the prover, want to show the verifier that M1 and M2 aren't the same. And both parties know what M1 and M2 are as a list of zeros and ones. And yeah, I'm going to let you struggle with it for a bit, draw inspiration from the coin problem if you can. And yeah. Any clarifying questions before I release?
You want to show that they represent different networks?
Yeah, that there isn't a permutation between
They
them.
can connect them.
Yeah. Okay?
There actually isn't.
Yeah. Okay. Yeah, you can assume that there isn't. And then we'll check whether what you come up with is convincing and is zero knowledge after you come up. Oftentimes it's good to try and come up with something that's convincing and then try to make it zero knowledge or something like this. I will say you won't have to go into any specifics about graphs or their matrices or anything. It'll be kind of a higher level logical thing. Okay, good luck. I'll come around and answer any questions you might have. It might help to have paper and pencil out, or if you don't have it, a friend of yours might, just to try things out.
Sure.
So then just to make sure I understand this correctly, the bigger
Did you say that both of them know both matrices?
Yeah. Yeah, so they have access to this matrix and this matrix. They both have them stored in memory, and they're talking about the same thing. Yeah.
The verifier knows they're different, and they want.
No. The prover knows they're different, and the verifier wants to be convinced that they're different.
That there's no permutation to get from M1 to M2.
Yeah. So just like I showed you, I convinced you that these two coins are distinguishable.
Yeah.
Well, I want to say that you want to prove that M1 and M2 are distinguishable.
Okay, so the prover needs to prove it in a way that is.
Yes.
Because if they sum up, they'll sum up. But
Yeah. So basically, both parts.
Which one does this
One, two. And the prover wants to convince the verifier that these are actually distinct. But they don't want to tell them more.
Say like there's one spot on the graph where they don't want.
I'm looking for two ones I want to convince so that I can distinguish these two things. Absolutely.
You have to have a function.
That I way of distinguishing. So the question is, what conversation should we have?
because they just take more.
Where if they aren't the same thing, I can tell the difference. Then I already show.
So by location.
Yeah, we're just guessing.
So what we can do is we have like
Yeah, you're trying to figure out what conversation you should have.
He's trying to bring up this, there's no, if they represent different numbers, there's no way that he could have permutated M1.
It's kind of creative represent the same. You should draw inspiration off of a coin example for what kind of coin.
It is the coin machine.
Challenge.
He just guesses over and over and over again.
The question is, what's
that
zero challenge? That what proves what's one of your responses on
there is zero. No, I think the response verifier just needs
exactly two. So we can make based on location.
Then
I agree with that.
yeah, it says
it's
to the prover, it says M1 is equal is M1 like verifier is M1.
I think you would say which graph did I change? Yeah, which graph? Like, the verifier takes either M1 and M2, does some sort of transformation to it. Also tells the proof no.
What do you do like a real test?
We have no, if it is part, we want to M1.
Yeah, we do it the same way. I just like how he switched them.
Right.
This was the reason we want to use
It's just a, yeah.
Yeah, but I think it's different in the classroom because you have the pattern that there's no connection. Whereas there he was proving that they are.
Okay, so hopefully you've struggled with it a little bit. It's okay if you didn't figure it out, but hopefully you're primed to think about other people's proposals, and we'll evaluate whether we like them or not. So, starting over here, what are y'all thinking?
Okay, I'm thinking on the fly.
Okay.
Verbally processing, but the verifier takes either M1, M2, transforms.
So they pick one of them at random, is that what you're saying?
Yes.
Okay, so they're going to pick a random bit, either 1 or 2. So B, which is picked at random, it's either 1 or 2. Okay, and then?
Makes some sort of transformation, maybe just like an additive transformation, some sort of transformation.
Okay, like you mean like shuffling
Permutes
the...
it or shuffles it or gives
Okay, so it takes the nodes representing MB, which is either 1 or 2, right? Whichever one they pick, they either pick M1 or M2, and you're saying that they make a shuffled version of that. So pi is now going to be a random permutation of the nodes, like the labels of the nodes, their names. Okay, and then what do they send over?
What do they send over?
Yeah, what do they give the prover? What's the challenge?
The result of that transfer.
Awesome, so they're going to take pi of mb. So b is the one that they picked. It's either 1 or 2. So they pick either m1 or they pick m2, and then they shuffle it randomly, and then they send that over. So this is, again, just a matrix with zeros and ones in it. Okay, and then how does the prover respond to this challenge?
You can tell which one was permuted.
Oh, great. Okay, yeah, they just guess what the b was. So we've got this m1 and this m2, and the verifier picks one of them at random and makes it look completely different by just reordering all of the nodes, and then hands it over, and then the prover has to say which one this was originally, which one they permuted, and they can just brute force it. The prover gets as much time as they want. Okay, so let's check. Is this convincing and is this zero knowledge? So to be convincing, what were the two things that had to be true of the conversation?
Dishonest prover may fail.
Okay, so if the prover is dishonest, which means M1 and M2 actually are the same, there is a way to relabel this to get this. Then, how often will the prover fail to respond to a challenge? Why? Awesome, yeah, if they're the same, the prover won't be able to tell which one you started with and shuffled up, because you're getting a random shuffling of this graph, but a random shuffling of this graph is also a random shuffling of this graph, because they're the same one. And so if you randomly permute one of them and they're the same, there's no way to tell which one you started with.
Does he pass on the permutation or no?
Oh, no, pi stays secret,
Okay,
b
pi
stays secret, and you just send over this thing.
Just the mutated.
Yeah.
Matrix, okay.
Yeah, we could call this M3 or something.
Yeah.
Maybe I should. So M3.
Pi could be like add 3 to every element or something.
Pi in this case is just permuting the labeling. Yes, that is important because if we did something else, then maybe you could distinguish which one it came from if they were the same. But if you take a random permutation of this is the same as a random permutation of this with a different permutation, because there's a permutation between them. So that's why we want pi to be a random permutation. But okay, we let M3 be a random permutation of the one that they picked, and we send over M3.
And is a random permutation, I switch columns 2 and 3. Like that
Columns and rows, right? Because the columns and rows. Yeah, it's like if I took my graph and I just relabeled in a certain way. 1 went to 2, 2 went to 1. Exactly. Yeah, and this can be done, for those who care, as a permutation matrix, and then you do a multiplication. So this is something that the verifier can do. It's very fast. It's a matrix multiplication. It's actually 2. But I don't want to talk about the math so far. Okay.
So the prover brute forces to find the permutation.
Yeah. So I'm just going to write brute force. Or maybe they're not brute forcing. Maybe they know something about the difference between M1 and M2, and they can they know some computation where if I do it on the matrix, I get a different answer for M1 and M2. And if two things are the same, I'd get the same answer. And so they do it on this one, and it'll spit out a number, and they'll know which one it is. But somehow they figure out which one was given to them, and then they tell. And the reason I wrote it like this is the stuff over here is stuff only the verifier knows, and the stuff over here is the stuff the prover knows, and then this stuff is the stuff that goes between. So, good question. Yeah, pi does not get sent over. If it did, it would allow a dishonest prover to succeed. So it wouldn't be convincing. Okay, so a dishonest prover might fail half the time, in fact. So that's pretty good. Will an honest prover always succeed? Why not?
Yes.
You could do it within a range.
Sure, they could make a mistake, but assuming, this is kind of like a theoretical framework, assuming that all the programs are written correctly and all of this, they always will be able to figure out which one it is given enough time. Okay, so it's convincing. Is it zero knowledge?
Depends on how many permutations are used.
Okay. So what is it that the verifier is given that they don't generate themselves? The only thing that they're given is this B hat, which if I have an honest prover is going to be equal to B. So this is actually just like with the coin situation. I'm only going to tell you things you already know. But I'm going to do it over and over again, and so eventually you'll become convinced that I can distinguish between these two things. But you don't actually get any information from this conversation you're having. Awesome, so we have our first little zero knowledge proof that two graphs are not isomorphic, are not the same, aren't a relabeling of one another.
But the example you gave, they are the same, right? The 1, 2, 3, and 2, 1, 3.
Yeah, the thing I wrote down here is that they are the same.
This would, that would.
Yeah, it would be like I would have to change this one a little bit and then ask or to prove that they're different. But this brings up a good point. Showing things are different, maybe that's just easier. My next question for you is, say that I have an M1 and an M2 and they're actually the same. So I'm going to erase stuff. Okay, so say that I have, again, M1 and say that there's an M2 and that they actually are a relabeling of each other. Say by some pi. So what I mean by that is pi applied to M1 gives you M2. Okay? Now this pi is known by the prover, right? They could brute force it, but more practically they probably generated it. Okay, they came up with a random M1, they generated a random pi, and that gave them M2. So you can think of M1 and M2 as a pair, as being the public key, these two giant matrices, and the private key is how to relabel this to get this. Now keep in mind, how many ways are there to shuffle like 100 numbers? It's a huge, it's 100 factorial. It's 1 times 2 times 3 times 4 times 5 times 6 times 7, and all the way up to 100. So it's like a huge number. So this is actually, again, going to be computationally hard to do. The verifier isn't going to be able to figure out what pi is just from M1 and M2. But the prover knows it, and okay, I want to prove that M1 and M2 are actually the same network without revealing anything about pi. I want it to be zero knowledge. So that's your next task. And I'll give you a hint or two. Basically in all of these zero knowledge proofs, it ends with the verifier sending a challenge and the prover responding to that challenge. Yeah? Just like we have been doing with these, and even with the sudoku, right? I sent you a bunch of encrypted stuff, and then you gave me a challenge, and then I had to respond to that challenge. So it's always going to end with the verifier sending a challenge, and then the prover responding. And I claim that to solve this problem, you're going to need one more thing to communicate. And it wouldn't really make sense for the verifier to send something, because I could just think of that as part of the challenge. So there's actually going to need something sent in that direction. I'll let you think about it, but okay. The question is, what conversation could a prover and a verifier have to convince the verifier that these two matrices are actually of the same network? I'll give you a good 5-10 minutes to discuss it in your groups. And again, both people know what M1 are and M2, but only the prover knows this pi. So you both have these coins, but this time they're actually the same coin.
So he's proving that they are a function.
This will be 1 and a half.
The verifier sends a bad one.
So I'll call this set.
So M1 and M2 are public, right?
Yes.
Oh, that's not.
Setup is a 1, 3, 2. Yeah, so he reveals a couple numbers in his solution. That's the solution is the margin. Well, the setup is that it's the solution. No, M1 and M2 are just the solution is the function. The number. It's really just right.
No. Yeah. Pi being yeah, it's meant to be a strip.
Is the permutation going to be a matrix?
Yeah, you can think of it that way. Yeah. Yeah, you take the identity matrix and then you permute it in the same way, and then you take that and its inverse and you multiply on both sides, and that's going to just do the permutation to the adjacency matrix graph. But you don't need to know those details. But yeah, pi is just this thing, it's efficient to work with. Yeah.
That's what I'm thinking somehow, so it's
So you should think of this kind of like we're working with coins, but the reason I've moved into this digital thing is two things being the same means there's like a way to transform one into the other. And so just like last time, you can generate new coins that are like copies of this one. Right? Like for showing two were different, what you did is you picked a random one and you made a copy of it. Right? And then I told you which one it was a copy of. So think of it, if you want to avoid thinking about details about graphs or matrices, because that way you're going to end up not being zero knowledge, I claim. Think of it as I have these two coins that are actually the same, but they're not coins in the sense that you can like make a copy of one of them that is a random copy of it. So that if these were copies of each other, for example, you wouldn't be able to tell the difference between them. Sorry, that was a bit weird, but yeah, anyway, my point is we should still think of them as kind of showing things are the same in kind of this abstract way. You don't want to think about the details of why they're the same.
That's what and then the verified permutation.
Yeah, and when I get stuck thinking about how could this work, I always ask like, what could I send that could be useful? Because most things, I mean, I could send a random number, but that's not going to be useful, right? You want to send, and so sometimes I don't start with the setup. I start with like what the challenge is going to be, and I work backwards. Just try and make guesses and fill things in. It'll be more of a creative process than an analytic one.
Yes, I got you. Aren't they all technically equal in representing the value? Yeah, say just like shift everything up. That will really different ourselves. So I just shift use some
Does anyone have any thoughts about what any of these three maybe should be, just to help brainstorm?
I think Prover can provide a permutation, not the permutation between 1 and 2, but some other permutation.
Okay. So say we have some other permutation, Greek letters, come on, of alpha. Great. Okay, so you have an alpha, and you're sending alpha, or you're sending alpha of something?
Prover is sending alpha.
Oh, okay. So alpha is just some other permutation.
and then verifier picks B. So verifier picks a bit,
Okay.
B, and then applies alpha to either M to MB,
Okay.
and then sends the result.
Okay.
So M, and then prover has to return B.
Has to return what? B. Okay, yeah, let's think about this. So the prover is sending over a random permutation, and the verifier is applying it to one of these at their discretion and then sending it back. If I'm a dishonest prover, can I win?
Yeah.
Oh, okay, that's not good. How do I win? Just in case anyone doesn't see it.
Apply it to both and see which.
Yeah, for example, I could just apply alpha to this and to this and see which one it's going to be the same as. Another way, if you know what alpha is, it's easy to compute with the opposite of it. You just flip all the arrows. 1 went to 2, now 2 goes to 1, etc. And then you apply it to M3 and you'll get one of these.
Can the prover break pi up?
That's a good question. Yeah, can the prover somehow like break pi up? You'll see why it's a good question when we have a solution, but I'm not sure that this will help us in getting a solution. So, good question, yeah.
Okay, can verifier add like an alpha prime? Add another transition on, a transformation on.
We could, but then we just get like one transformation at the end of the day, right? It might be.
But prover doesn't know that transformation.
Oh, I see, I see. Let's see. So actually, I kind of like something like this, but what if M3 was actually something the prover sent to the verifier?
It's another point.
Right? In some sense, sending a random permutation that we now both know, that could have been sent as part of the challenge. Like the prover isn't really providing anything. It's kind of like sending over a random number to start. So what if instead they kept alpha to themselves and they sent over M3? Now, this is like a new coin that's a copy of these that we claim are the same. So we just have some third coin. All right, M3 equals, say, alpha of M2. It doesn't matter which one you pick, they're the same. Okay, so we sent M3 over. What could a challenge be? So I've got 3 coins now. I claim that they're all the same. And the third one is just a random copy of, I claim both of them. What kind of challenge could I give to a prover where if M1 and M2 were actually different, they might fail?
Some information about alpha.
Yeah. What kind of information?
Like a row or something that resolves to a part of M3.
Okay, let's think, backing up for a bit. If I just give, as a response, all of alpha, that's going to be okay. Like, I can give all of alpha, because it's random.
Pi and alpha together, and then apply the whole to M1.
Mhm. True. The prover could do that.
Would that reveal anything if he gave the combined?
Yeah, this is a good question. So if I have this secret pi, right, a secret relabeling of M1, which gives me M2, and I have this random relabeling, alpha, which applied to M2 gives me M3, if I take alpha and pi and I put them together, right, you should think of this as a matrix that is secret and a random one, and I multiply them together, the result will be a random matrix. It's kind of like if I have a secret number and I have a random number and I add them together, I have the same chance. If I think of a random number as like, I'm going to pick one at random from a set of numbers, and then I ask like, what is the chance I get this as the result of the sum? I get the same chance of ending up with any number. If you add a random number to something, you get a random number. It kind of destroys all the information for someone who doesn't know the secret. So yes, it's actually okay to compose alpha and pi and send that over.
It reveals nothing, but it allows them to prove that M1 can be mutated into M3.
Ah, yes. So kind of what I'm hearing is we're thinking the response should either be alpha or pi followed by alpha, like putting them together. What would be a challenge to which this is a response?
So you have M3.
So this alpha shows that.
They don't know alpha. They don't know pi. But they know M1.
Or actually, what does alpha do? Alpha, so I have M1, M2, and M3. And we know pi goes from here to here, and alpha goes from here to here.
So
And this is like alpha with pi.
So the verifier can give M1 or M2.
Got you, yeah. So they're going to generate a random bit like earlier, and they're just going to send it over. They're going to be like, the prover sends over M3. The verifier is like, show me that M3 is the same as, and then either M1 or M2. And if they say, show me that it's the same as M2, then you just send alpha. So if B equals 2, then you send alpha over. And then the verifier just checks that alpha applied to M2 gives me M3. And if they asked you to show that M1 and M3 are the same, you send over this product of pi and alpha, which sends M1 through here, down here to M3.
So you can't reverse the alpha transformation and extract pi.
Because they don't know alpha or pi.
They only know the pi.
But if you do this iteratively,
Well, the thing is, it's important that alpha gets picked newly and randomly each time. That's exactly right. So that'll be important. So if I do this once, you've learned nothing because either I've given you a literal random matrix or I've given you a literal random matrix. I mean, it looks random because I've added a random number to it.
What does the verifier do in the second case with the alpha?
Yeah, so they just take M3 and they apply, so I need, say beta is the name of the permutation that gets sent over. Then they just check that beta of MB equals M3. So if they sent over 1, they check that beta applied to M1 gives them M3, and if they sent over 2, they check that beta of M2 is equal to M3. So I have my 2 coins, I generated a third random one, and then you're allowed to ask me, show me that it's the same as this one, or show me that it's the same as this one. And if my original 2 weren't the same, it can't be the same as both of them, right? And so you have at least a 50% chance of getting me to fail, because there's not going to be a response to that challenge.
You need both, or will either one prove it?
What do you mean?
Like both challenge types would be.
Yeah, you'll want to pick randomly, because if you always just pick like 2,
You have to ask multiple times.
like if the prover can know what the verifier is going to do each time, then they can always make it so that that is the alpha. They don't have to follow the
I'm
rules.
just saying, is one set of these communications enough to prove or get?
Well, or one set of these communications, like with the coins from earlier, you should think of as getting you like 50%.
Gotcha.
Sure, and then you do it again.
Doing it, and it would increase your
Yep, and now it's 75. Well, the chances that I succeed each time if I'm dishonest are 1 over 2 to the n. Like it goes to 0 very quickly.
So after n number of rounds, you can be pretty sure that it's.
Yeah, if you do it like 100 times.
Gotcha.
This leaves pi, doesn't it?
What's the question?
Doesn't-
So since alpha changes each time, alpha with pi together is like taking my secret and adding a different random number to it each time. And so the result is just always a random number. But this is a good question. Like, how can we
The
be?
challenge is 1.
So,
So like here, like our challenge is
so if the challenge is 2, you give them alpha, which is just a random thing you generated
what if
for
the
this.
challenge is 1.
And if the challenge is 1, you give them the product of alpha and pi. So alpha being the random thing, pi being your secret.
SS. And you just never take pi. Okay.
Yeah, but that's the question. Like, how can we be sure that we're not leaking any information? So let's come up with a better definition of what it means to be zero knowledge. What did I mean by nothing useful? right? Like clearly, unlike before, the prover is sending things to the verifier that they didn't already know in some sense, right? Like they didn't have those matrices. Okay, so here's how I'm going to define zero knowledge. Like I've kind of been pointing at, it's going to involve the communications between them and whether the verifier can do anything with that they couldn't have already done. So we want to say that it's zero knowledge if the verifier can simulate the prover in the sense that they can generate these transcripts without a real prover around. Because then anything they could do with a conversation with the prover, they could do on their own. They can generate their own random numbers, this kind of thing. So okay, what is a transcript for this particular example? It looks like a triple M3 B beta, right? It's a matrix, a bit, and then a permutation. That's what the transcript is of one of these conversations. And you should really think of like a list of transcripts. And if it was true that the verifier could generate their own list without a prover, and that if you gave these two lists to someone, they would not have any way of distinguishing them, then anything that the verifier could do with the actual transcript, they could actually just do with the fake one that they generate on their own. And so that would be what we mean by zero knowledge. Nothing useful, because they can't do anything with it that they couldn't already do. Okay, so what do I mean by generate something that looks the same? I mean that when I talk to the prover with the verifier, they have like random numbers being generated, right? Alpha came in randomly, B is random, and then beta is somehow fixed by those. But if I don't think about the order in which they're created, like if I take a transcript and I just look at M3, it's going to be sampled randomly from permutations of M1, or sorry, of M2, I guess. And B, if I don't look at the others, is just a random sample of 1 and 2. And what about if I don't look at these, and I just look at beta, the betas I get each time? That is also going to be randomly sampled from all permutations of the number of nodes that I have, the number of labels. So individually they're all random. Of course, when I have the triple, it's random subject to the constraint that beta of MB equals M3, right? So in some sense, I have 2 degrees of freedom because I have to satisfy this. Okay, so how might I forge a transcript without talking to a prover? Well, what I'll do is I'll pick B. I'm the verifier. I know which B I was going to pick. I sample it randomly. And then I sample beta randomly as just a random permutation. And then how do I pick what M3 is?
Reverse.
M3 has to be subject to the constraint that it's beta of MB. And I have beta, and I have B, and I have M1 and M2. So here I just put beta of MB as my M3. Right? So I just generate a random bit, generate a random permutation, and then I just compute this. And if I write down a list of these generated things, and I write down a list of transcripts with an actual prover, they're sampled from the same set with the same distribution. There's no way to distinguish between these two things, these two lists of transcripts. They're actually sampling from the same set. So in some sense, I don't get anything from talking to my prover because I can sample transcripts without a prover by just going backwards. And this is kind of a formal way of reasoning that sending over random numbers in this kind of way is actually safe. You're not going to reveal anything because they're not able to do anything they couldn't already do. It's not revealing anything about our secret. So that's what zero knowledge means, is it means that the verifier can simulate a conversation with the prover. Not in the right order, usually it goes backwards, but anything that they could have done with real conversations, they can do with these fake conversations, right? The data of a fake conversation is the same as the data of a real conversation. And that's what zero knowledge means. So, for example, with the coins, how it went was you handed over something, and I told you what it was, right? It was like that pi of C1 B hat. And a verifier can generate those on their own, right? First, they pick what the response is going to be, and then they generate whether or not they swapped them, and they do that randomly. Yeah?
So the verifier doesn't have any assurance that pi was the same every direction?
This is true. This is a good point. All it proves is that M1 and M2 are the same, but there is kind of this other math I'm not going to go into, in which you should actually be convinced that the prover does know a way of getting from M1 to M2.
That's why you have to keep going over.
But they might, okay, in this case, there is actually only one way to go from M1 to M2.
Because we picked matrices?
Because I'm talking about graph isomorphisms, and those are unique. Yes.
Okay.
But in general, in many contexts, when you're proving knowledge of something, like for the Sudoku puzzle, I could be putting down a different solution each time, and you'll still verify it correctly.
Yeah.
But I'm proving that I know at least one solution, is kind of what I'm proving. That's a good question. Yeah, and just like similarly, let's think about whether the Sudoku thing was zero knowledge. You would start by knowing whether you're going to pick rows, columns, the setup, or the square. So you put that in the transcript. And then, if you were going to pick rows, you make it so that the rows are a random number between 1 and 4 in each thing. Or if you were going to pick columns, you make those random numbers between 1 and 4, without it being a real solution. Because everything's encrypted, that isn't revealed. And similarly, if you were going to check the setup, you pick a random permutation, and then you just put stuff down in those things, and then you put garbage everywhere else. So the transcript is something you could have generated, and that's what makes it zero knowledge. Okay, so I've been talking about graphs, and I mean, we care about those, you know, lightning network, all these kinds of other things, but we don't really care about graph theory so much, unless you're trying to compute routes. Anyway, it's not relevant really to us. So I would like to kind of pivot and see if from this, I can come up with Schnorr signatures. Because a Schnorr signature really is a zero knowledge proof that I know the private key to a public key. And here I claimed you can think of M1 and M2 as being the public key, and little pi as being the private key. Okay, so I'm just gonna, in place, start erasing things on the board and replacing them for showing you what the zero knowledge proof is that I know the private key to a given public. Okay, so instead of M1 and M2 with pi, I have a little secret, little x. That's just a number, my private key. And then I have my public key, which I'll write as a capital X with these bars. And that's just equal to little x times the generating point of my elliptic curve. If you know what that means, it's just saying that I take the public key for little x. That's what that times g means. It's just take the public key. That's a g, not a 6. Okay. And then the prover is going to generate a random nonce, a random number. I'll call it little k. And they're going to send over. Sorry, I should have written this here because that's what it was replacing, right? But anyway, I'm going to write this little k, and then capital R is just the public key for k. And you send over that public key for this random nonce. Okay, and that's my setup. Just like before, I'm taking like a random thing, I'm putting it through, you know, I'm not just sending little k over, that wouldn't do anything. I'm sending the public key for k over. All right. And next, the verifier in our previous case sends over a random bit. Here they're going to send over just a random number called the challenge, usually denoted E. Since it's not a bit, I won't use B, I'll use E. Okay, just a random number. K is a random number, E is a random number. Okay, and if that's the challenge, what's the response? Well, it has to use the private key in order to be something we should care about. So I'm going to take x times E, right? I'm going to put those things together. But the problem is I can't just send over x times E, right? Because they know what E is. They're just going to divide by it and get x, okay? so what I'm going to do is I'm going to add my random number to it. Right? If I add a random number to it, now it's just a random number. They don't know what k is. I'm going to send s over. And how will the verifier know that this s is actually legit? They're going to take its public key. They're going to compute the public key for this number. And what's that going to have to be equal to? It's going to have to be equal to the public key for k plus the public key for x times the challenge. Right? So they're going to take this response and see if its public key is what it should be, because they can compute what it should be from just public information. And I'm not going to do it here, but you can prove that it's impossible to send a good response unless you actually have knowledge of little x. It's not a long argument, but like I don't want to get into the mathematical weeds. I wrote a couple blog posts if you want to go read about that. The specifics of why it is that s can't be gamed. It actually requires knowledge of little x. But that's what makes this convincing. Okay. What makes it zero knowledge, or sorry, what makes it, if I'm an honest prover, I can always succeed. I just follow these rules, it'll work out because of the math. Okay, what about zero knowledge? A transcript is RES, where all of them are random, like before, if you looked at them individually, but there's the constraint on the triple that S times G equals R plus X times G. That's the constraint. So this was from a real conversation. How would a verifier simulate this? Where do I start? If I'm trying to construct a triple that is indistinguishable from a real conversation.
Well, E is random.
Sure, yeah, E is just going to be a random number that I would know anyway, and then S is also just a random number. So I'm hearing some E's, I'm hearing some S's. Yeah, let's generate those two.
You generate
as random numbers.
mods and then multiply that by.
Well, in particular, I need R now.
Yeah.
So let's subtract this over and solve for R. So this constraint is the same as the constraint that R is equal to little s times G minus little e times x. And I've picked an S and I've picked an E. And G and X are just public information. And so I can compute R. So right here, I just put S times G minus E times the public key.
So I know you said this before, but what exactly is that doing? Because the replayability is just showing that.
Yeah, so essentially if I talk to a real prover, I'll get a list of these things. That's what I get information-wise.
Yeah.
This is all the information I get from a real prover. But I claim that this is just sampling from the set of triples, R, E, and S, where R is a random point, E is a random number, S is a random number, subject to this constraint. Right? I have an equal chance of getting any triple, so long as that's true. Like I carve out that subset of triples. Just any public key, any number, such that this is true. And I'm just sampling randomly is what I'm doing when I'm talking to.
But of course it's true, you're generating it. So what is that?
It just proves that no information is leaked.
Yeah, so anything that I could do using this, I could actually also do using this. So I've learned nothing useful.
So why have the conversation?
Yes, why have the conversation? Because this is zero knowledge and it gives you nothing. You're just generating stuff. This is giving you nothing other than the fact that the prover knows the private key to this public key. Right? A zero knowledge proof is where you learn nothing other than the statement being proved. So this is a way to convince a verifier that the person they're talking to owns this public key.
Is the transcript mostly helpful for understanding, like, I don't know, design space, like the set of all possible answers or a set of all possible inputs? If the prover was to somehow make that set smaller, then they're leaking information.
Or if they're sampling from a different distribution on that set or something like that. Yeah. Exactly. Yeah, this is just a tool we're using to argue why we're not leaking any information about our private key.
Yeah.
Yeah, because anything that they can do after talking to us, they could have done without talking to us. because they can generate their own transcripts. And so that is that's how you argue that they don't actually know anything about our private key from doing this. Because if we're assuming that they know nothing about our private key just by knowing our public key to begin with, and that doesn't change. Okay, so I claimed that this was the Schnorr digital signature, but like this requires back and forth, right? Like it's a way, this is called the Schnorr ID protocol. It's a way of proving that you know the private key to a public key. That you are who you say you are if you treat public key as an identity. And you could have viewed our last zero-knowledge proof of showing two graphs are the same also as an identity protocol. I am the person who knows how to turn this into this. So anytime you have a computationally hard problem, you can make this setup challenge response protocol, and that gives you an ID protocol. Am I out of time?
No, you've got like 15 minutes.
Oh, awesome. Great. You know I can do good with 5. Okay, so, all right. What is it that the verifier is really providing here? They're just giving us a random number, right? They're not doing anything complicated. What could we replace them with that's deterministic but spits out random numbers? Hashes. Yeah, so what if I replaced my verifier with a hash function? What would it take the hash of? Well, it has to take the hash of kind of everything we have around, like the context. Stuff that I can't finick with. So, erasing my transcript stuff for a moment, now that we're convinced this is zero knowledge. What I'm going to do is I'm going to modify this proof, and I could do the same with sudoku, because you were just giving me a random number between 1 and 4. And I could do the same with graph isomorphism, showing two graphs are the same, because you were just giving me a random bit, right? So here I'm going to say E is just going to be the hash of everything in the context. In this case, capital R and capital X, right? I'm just going to take this hash of the information that's lying around. And then that's what E is going to be. So when I'm the prover, and I want to prove that I know this key, well, perhaps I should also put in here like the statement being proved. Like, Nadav knows private key to capital X, or something. Cool, so I'm just going to hash some stuff. I've got this message that's in the, yeah?
Why do you verify to type and say?
True, but I'm replacing the verifier with a hash function. And the question is, what should it hash? Because I want it to just spit out random numbers. And I don't want to actually talk to someone to get those random numbers, but we want to make sure that the prover doesn't control what the random numbers are, i.e. not so random numbers. And so we're forcing them to use a hash function, and then we're going to hash R, we're going to hash X, everything in the context.
Why do you need to prove the public key? Why do you need to hash the public key?
You don't, but we do in Bitcoin. And in general, it's good practice to put stuff in the context in the hash. But technically speaking, R will end up being enough. But in general, as I said, like, you should put the whole context in there, just to be safe. But if you do some math and analysis that I'm not going to do for you here, it'll turn out you could hash R in the message, and that would be enough to make it secure. But RX in the message also fine. Sorry, I heard another question?
So why are you trying to get rid of the verifier?
Because I want to make it non-interactive. I want the prover to just be able to generate an ID protocol output that can be verified, i.e. a digital signature, right? A digital signature is just a non-interactive ID protocol. Awesome. Okay, so I've replaced the verifier by just this hash function. So when I'm the prover and I want to go sign something, and perhaps I want to sign like a message, like a transaction also, whatever's in the context of what I'm trying to prove, I throw into that hash as the message. And then I generate my random K, I generate R from that, just like before. I compute E, instead of talking to a verifier, I talk to a hash function, which I can just do on my computer. I don't have to go to a network or anything, I don't have to be online. I just compute this hash, and then I compute the response to that hash. And now what I have to make public is I have to tell people what my setup was, what my R is, and And they already know my public key, it's public. And I give them S, my response. So my setup and my response. And from my setup, they can compute the challenge themselves, right? They just take the hash of R and the context and the message, which is part of the context in all that. And this can then be verified by computing E from that, and then checking that S times G equals R plus E times X, where E is this hash. And if that verifies, it's the same as if like we had an actual conversation. Now perhaps you shouldn't be fully convinced, like how do we know? Because there's a bunch of math that I'm not going to tell you about. But you can go try and read my blog post. It's a little complicated. But if you go to shirtbits.com/blog, shirtbits.com, you go to their blog, and you go to the cryptography section. There's a series about Schnorr signatures, and the first 2 posts are kind of going to go through the mathematical details we didn't go through here today. But okay, we have this zero knowledge proof, and anytime we have this kind of one way, and back, such that this is just a random number being sent over, you can replace it with a hash. And that makes it non-interactive, and it turns an ID protocol for any computationally hard problem. We could do the same thing for graphs or for sudoku or anything like this. And it turns it into a digital signature, showing that I'm the person who knows the solution to that hard problem. In this case, I know the discrete log of this public, the private key to this public. And then you just publish the setup and the response, and then people can verify by computing the challenge themselves.
So if you're doing a digital signature, you need basically one more private key, public key pair. If you're going interactive,
You're talking about this?
Escape.
Yeah.
If you're going interactive, then the other side to participate, they need their own private key, public key.
No, the verifier doesn't need any private key, public key. They just generate a random number. And here we've replaced them with the hash.
But that's their number that they get.
Yeah.
So for every party that you want to add to this, does that mean that you need to add one more number?
What do you mean by pub key that I want to add to this?
So when you had just one party over here, you had one extra number K.
Yeah.
When 2 parties, you had E.
Yeah, so in both cases I have E, but in one of them it's a random number generated by the verifier, and in the other case it's a random, pseudo-random number generated by a hash.
If you had to do something between 3 parties,
Okay.
I'm not quite sure what that would be yet, but they basically get 3 different people.
I see, yeah, so if the prover wanted to convince 2 verifiers that they knew something, they would do it once with this person, once with this person, and both of them would have to generate random numbers.
Exactly, so every extra person or every extra party in this basically needs to add a number. As long as they add a number in there, and then you can do the computation on it, that's how it works.
Yeah, the verifiers are just generating a random number in all of these zero-knowledge proofs we've talked about today. And that means we can replace them with hash functions and get rid of verifiers in the actual construction of the proof altogether. All you have to do is verify the proof at the end. And that's what a digital signature is. And in fact, what I have on the board here is the actual Schnorr digital signature that Bitcoin uses. It is going to be an S that's equal to a K plus X times this hash, minus maybe this. Just the transaction is good enough. Because we all understand that this means that the person who knows the private key to this public key has signed this transaction. So perhaps I'll transaction, usually like hash or something. Great. So this is the actual E that we use, and this is the actual digital signature that goes on chain. This R is the first 32 bytes, and this S is the next 32 bytes.
So is there something different between this and the other examples we talked about, other than that guessing X is way harder than guessing 1 or 2 from 1 to 8?
Yeah, so one thing is that this hard problem is much better studied. Like, graph isomorphism is not known what complexity class it lives in, which I guess is the same for the discrete log, but not many people study it. It's not hard in general. You want a problem that's kind of hard in the average case. There are a lot of special cases where it's easy to tell when 2 graphs are the same, and far fewer in this context, so you can actually use random generation. And generation isn't as hard. The other reason is that you can do cooler math on these things than graphs with permutations. For example, I can add two of these s's together from different things, and I'll get something that kind of looks like an s. It'll be the sum of the two k's plus x times the sum of the two e's. So there's all sorts of other kind of desirable properties, plus it's the cryptographic assumption we're already using everywhere else in Bitcoin. It's, kind of, if you're going to use the discrete log problem, this is probably the signature that you're going to use, if that's your cryptographic assumption, because it's the nicest one. Any other questions? How much time do I have? I have a couple minutes. Okay, so I'm just going to say a couple more general things about zero-knowledge proofs. So we've talked about what they are, and we saw that in general, they oftentimes have this kind of, you set in a setup, you get a random challenge, and then you get a response. So same thing happened over here with Sudoku, right? I set it up by writing down, or giving you a bunch of encrypted information after doing a permutation and some other stuff, and then you either ask me to reveal the rows, the columns, the squares, or my setup, and then I respond by giving you the keys to decrypt. I flipped over those things. And we could do that over and over again, or many times all at once if I did it using hash function instead of you. But when is it that we can do one of these? Well, it turns out that Sudoku is like computationally hard in like a serious sense, in a way that we don't actually know about this or graphs being the same or different. Sudoku is known that every problem in NP, every problem that can be checked efficiently. So if you give me a solution to the problem, I can check it efficiently. That's kind of a class of how hard a problem is. It's harder than being able to compute a solution efficiently, we think. Yeah, it's called NP. And so for example, the private key, public key problem is an example of this, because if I give you my private key, you can very efficiently check that this private key computes to that public. And if I give you a solution to a Sudoku problem, you can very efficiently check that I've satisfied all the constraints. And that's harder than actually computing the solution. Verification should be easier than the actual computation. If you know otherwise, then you can be a millionaire. There's an open bounty on that problem, but okay, we're going to assume that this is true. And anytime that that's true, anytime that just revealing all of your private keys would let you just check something very efficiently, there's always going to be a way to do this 1.5 round zero-knowledge proof, and you're going to be able to like replace this random challenge with a hash function. And the proof is just, I claim that some other mathematician out there has proven that any problem that can be checked quickly, you can take that problem and turn it into a giant Sudoku puzzle, where a solution to the Sudoku puzzle, there's like a dictionary going back and forth. They turn kind of the problem statement into a Sudoku puzzle, where a solution to that Sudoku puzzle can be translated into a solution to the problem statement that you started with. And so in theory, and that can be done efficiently. So in theory, what you could do if you have any problem is just translate it into Sudoku, do exactly the demo that I did for you at the beginning, demonstrating you know a solution by translating your solution into Sudoku terms, and then you'd be good to go. And that would be one of these protocols. Of course, this is not practical. I said efficient, but I meant polytime. That could mean like n to the 100 or something. So in practice, people spend a lot of time researching efficient ways of proving things, but just theoretically, if you're like, it would be so nice if I could prove that I followed some set of rules, but I used secrets, I can't tell people them. It turns out that anything that you can prove to someone, by revealing all of your secrets, there theoretically is a way, guaranteed, to do it by revealing nothing about any of your secrets. So there's this paper from 1990 titled All Things Provable Are Provable in Zero Knowledge. And that's a big result, but doing it efficiently is active research. People do that today. They make crazy money from VCs for trying. It's great. Any questions? Yeah.
So this is not quantum resistant. Is there a zero knowledge proof that is quantum resistant?
So the thing that isn't quantum resistant here is the actual underlying hard problem. but specifically not the NP part, but the discrete log problem for elliptic curves is not quantum resistant. And you could just pick a different cryptographic assumption that people think is, like learning with errors on lattices or some other problem, and then you could construct a zero-knowledge proof for that. It still lives in NP.
So what are we using in Bitcoin right now?
We're using this. We're using the discrete log problem for elliptic curves.
So the shift goes down and all goes down together.
I suppose so. I mean, you know, we've shown we can add new digital signature algorithms to Bitcoin. So, you know, Schnorr wasn't on Bitcoin until a couple of years ago. So we can add other signatures if we want. Any other questions? Awesome. Well, it's been a blast, and hope you have a good last day of TabConf.